we found the strongest evidence to date of possible biological activity on an exoplanet.
In September 2023, the James Webb Space Telescope quietly sent back a signal that shook science itself. Hidden inside the light of a distant world called K2-18b, astronomers found something they had only seen on one planet before, our own. Among the layers of hydrogen and vapor surrounding that world, Webb's spectrometers detected traces of dimethyl sulfide, or DMS, a molecule that, on Earth, is produced only by living organisms. The data wasn't a rumor. It came from NASA and ESA's official Webb analysis, later confirmed in Nature Astronomy, with a 99.7% confidence level, a margin of error so small it rivals the discovery of the Higgs boson. K2-18b orbits a red dwarf star in the constellation Leo, about 120 light-years away. Its atmosphere holds water vapor, methane, and carbon dioxide, while its temperature stays around 120 degrees Fahrenheit, warm enough for oceans to exist. If these readings are real, they mark the first chemical whisper of life beyond Earth. But here's the part that no one can explain: why scientists, after confirming such a discovery, suddenly went silent. So what exactly is K2-18b, and why has this planet made even the boldest astronomers so cautious to speak? The world that James Webb just revealed is unlike anything we have ever imagined calling habitable. K2-18b is roughly 8 times heavier than Earth and more than twice its size. Astronomers call it a Hycean planet, a hybrid between a hydrogen-rich mini-Neptune and an ocean planet. Beneath its thick atmosphere, there may be a global sea stretching for thousands of miles, wrapped in clouds of vapor and methane. Its skies glow faintly blue-green in simulation models, a place where sunlight filters through gas instead of air. Unlike our world, K2-18b circles a red dwarf star, a tiny sun that burns cool and slow. These stars can live for trillions of years, far longer than our own, which means life there would have more time to evolve, millions of centuries more. Each orbit lasts about 33 Earth days, placing the planet in the so-called Goldilocks zone, where liquid water can exist. But that's where the similarities end. Its pressure could crush a human submarine, and its skies would taste of hydrogen and salt. Even its daylight would fade to a permanent twilight, dimmed by the red star's glow. This is exactly the kind of world James Webb was built to find. With its infrared instruments, it can read the fingerprints of molecules in alien atmospheres: oxygen, carbon dioxide, water, methane, and now something far more complex. For decades, scientists assumed life would thrive only on Earth-like planets, rocky worlds with nitrogen air and blue oceans. But K2-18b challenges that rule. It suggests that life might bloom in places once thought impossible, in seas of gas, beneath hydrogen skies, far from any familiar warmth. The discovery also rewrites what life itself could mean. If DMS truly exists there, it might come from organisms that don't breathe oxygen, that feed on methane instead of sunlight. It might mean biology has found a second recipe, one that doesn't need to look or behave anything like us. NASA's team, led by Professor Niku Madhusudan at the University of Cambridge, called the data extraordinary but preliminary. Even so, they admit the pattern is clear. Every chemical signature lines up with what, on Earth, is made only by living things. That's why the world's telescopes have turned toward Leo, waiting for Webb's next observation window. Because if this signal holds, we're not just looking at another planet, we're staring at a new definition of what it means to be alive. And here's the twist that no one can shake. If this really is the first life we've ever found, it doesn't look anything like us. When the first batch of James Webb's raw data from K2-18b came in, scientists expected the usual. Water vapor, carbon dioxide, maybe traces of methane. Those are the standard ingredients of a potentially habitable atmosphere. But what they didn't expect was a pattern that mirrored the chemical balance of our own planet. A condition called disequilibrium, something that normally appears only when life is at work. The telescope's infrared spectrometer broke down the starlight passing through K2-18b's atmosphere, isolating each molecule by the color of light it absorbed. The readings were crystal clear, strong signals for H2O, CH4, and CO2, a combination that could allow a stable ocean beneath the haze. But then, in a section of the spectrum between 3.3 and 3.6 microns, something unexpected appeared: the telltale curve of dimethyl sulfide. On Earth, DMS doesn't come from volcanoes or lightning or even industrial processes. It's released almost entirely by microscopic plankton in the oceans. Life so small, yet so widespread, that it literally perfumes our planet's air. Seeing that same molecule 120 light-years away was more than shocking. It was almost unthinkable. The Webb team at NASA's Goddard Space Flight Center ran multiple checks to rule out false positives. They accounted for dust, for instrumental noise, even for contamination from Earth's own atmosphere. But the signal persisted. Every test confirmed the same peaks, the same molecular fingerprints. At a 99.7% confidence level, the presence of DMS became almost undeniable. That alone would have been historic, but there was another strange clue hidden in the data. Normally, planets rich in methane also show large amounts of ammonia because both are common byproducts of chemical reactions in hydrogen-dominated worlds. Yet, in K2-18b's case, ammonia was nearly absent. It wasn't missing by accident, it looked like it was being used up. That imbalance, according to the Cambridge research team, suggests an active process inside the atmosphere. Something constantly consuming ammonia while producing methane and DMS. On Earth, that's exactly what living microbes do. They breathe methane cycles, turning one compound into another, keeping the atmosphere out of balance in a way that can't be explained by geology alone. This chemical disequilibrium has become one of the strongest biosignatures known to science. When chemistry refuses to settle into balance, something is forcing it to change, and that something usually means life. Still, astronomers are cautious. DMS could have a new, unknown origin. Perhaps chemical reactions deep in the planet's oceans mimic biology without being alive. Or perhaps, as some quietly suggest, the molecules aren't being formed, they're being regulated. Because if nothing living is responsible for this pattern, then what else could be altering an entire planet's atmosphere? At first glance, K2-18b sounds almost welcoming. A world with water vapor, a stable temperature of about 120 degrees Fahrenheit, and the faint promise of oceans glimmering below its clouds. But this is no tropical paradise. Beneath the calm readings lies an environment so alien that a human being would not survive a single breath. Simulations based on Webb's data suggest that K2-18b is wrapped in a dense, hydrogen-rich atmosphere tens of miles thick. The pressure near its ocean surface could be hundreds of times stronger than Earth's, enough to crush steel or vaporize any lander that tried to descend. Below that, scientists believe lies a global ocean stretching hundreds of kilometers deep. Far deeper than the Mariana Trench, dark and slow-moving, with layers of superheated water turning to ice under crushing weight. Light from its red dwarf sun never truly brightens the sky. The entire world would glow in a deep amber hue, as if trapped in an endless sunset. Plants as we know them could never survive there. Photosynthesis would fail under such dim light. Yet, in theory, something else could thrive. Microbes feeding on chemical energy, harvesting heat instead of sunlight. And that's what makes this world so fascinating. The red dwarf at its center, K2-18, burns with incredible efficiency. It consumes its fuel so slowly that it could live for trillions of years. That stability means K2-18b has likely remained in the same gentle orbit for billions of years. No violent temperature swings, no catastrophic seasons, no global extinctions. It is in many ways the most stable environment imaginable for life to quietly evolve. But stability has a price. The hydrogen atmosphere blocks much of the visible light, creating a greenhouse effect that locks in heat. The air is thick, heavy, and likely toxic. Every sound would travel slower, muffled by dense gas. If you looked up, you wouldn't see stars. Only a dim crimson halo where the red dwarf hangs, barely cutting through the haze. To us, it would be hell. But to something born there, it could be home. A place where time itself moves differently, where evolution unfolds in slow motion over eons. A planet that doesn't need continents, forests, or blue skies, only persistence. If life has taken root in that endless ocean, it might look nothing like anything from Earth. It might live in pressure, breathe methane, and never once see the light of its sun. And that's the question haunting scientists now. Maybe life doesn't need land at all. Maybe it just needs endurance, a planet that refuses to change and the infinite time to adapt. Called 2-18 doesn't spin the way Earth does. It's what astronomers call tidally locked, meaning one side always faces its star while the other remains forever in darkness. There is no sunrise, no sunset, no cycle of day and night. Instead, the planet is divided into three eternal realms. A hemisphere of endless daylight, a hemisphere of unbroken night, and between them, a narrow twilight zone where the two extremes meet. On the day side, temperatures could climb far above 120 degrees Fahrenheit, enough to boil the upper layers of its hydrogen atmosphere. The red dwarf burns dimly but constantly, pouring a steady glow that paints the sky in shades of copper and blood. The ocean below would shimmer with reflections of deep crimson light, its surface restless under the slow pull of gravity. No clouds would drift there for long. The heat would rip them apart, driving storms that could last centuries. The night side, by contrast, is a frozen abyss. Without a single ray of sunlight, the atmosphere cools and condenses, forming towering clouds of methane and carbon ice. Temperatures may plunge hundreds of degrees below freezing. Here, winds scream toward the lighted half of the planet, circling endlessly around the rim of eternal shadow. It is a landscape of silence, a world where time itself seems to stop. And yet, right between those two extremes lies a region scientists call the terminator zone. The ring of perpetual dusk. Here, the light never fades completely. And the darkness never wins. Computer models suggest that this thin band, stretching thousands of miles around the planet, may hold the perfect balance of heat and cold. It's where water could remain liquid, clouds could form, and energy could flow just gently enough for complex chemistry to survive. In that half-light, life might find its refuge. Imagine an ocean horizon glowing under a red star that never sets, where every wave reflects the color of sunset. There would be no rhythm to mark a day, no clock to define time, only the soft, steady hum of a planet breathing through eternity. To a visitor from Earth, this would feel like a dream or a nightmare. The light never changes, the stars never move, and the horizon burns forever at the same angle. It's a world that doesn't sleep, doesn't awaken, and doesn't end. Scientists believe this twilight band could be the true cradle of life on K2-18b, a permanent in-between where warmth and cold reach a fragile truce. a world where dawn has never ended and night will never fade. If life truly exists on K2-18b, it almost certainly doesn't look green. Under the dim crimson glow of a red dwarf, photosynthesis as we know it would fail. The light is too weak, its photons too low in energy to feed the chlorophyll that turns Earth's forests emerald. On this world, sunlight barely penetrates the hydrogen clouds. What little escapes would reach the ocean as deep red and infrared waves, a spectrum invisible to the human eye. So if something lives there, it would have had to evolve a completely different way to capture light. Scientists call it red-shifted photosynthesis, and instead of green, the pigments would be black, violet, or indigo, tuned to absorb every last scrap of energy from the faint star above. Imagine vast microbial mats covering the ocean surface like dark velvet, feeding on warmth and infrared radiation. In such light, the color green would be useless. The survivors would have turned black to live. This isn't just speculation. On Earth, we already see creatures that thrive in similar conditions. Deep-sea bacteria absorb heat from hydrothermal vents instead of sunlight. Some purple sulfur microbes in volcanic lakes use infrared light to power their chemistry, proving that biology doesn't need the full brightness of a yellow sun. K2-18b could be the same, an entire biosphere built on shadow, not shine. It's a strange thought, a living ocean that looks dead to our eyes. From orbit, Webb might see only a dull, featureless surface, yet beneath it, countless black pigmented cells could be quietly multiplying, breathing methane, and shaping the planet's strange atmosphere. The DMS signal we detected might even be the chemical echo of those organisms, rising from a sea that never sees daylight. This turns the search for life upside down. For decades, humanity has looked for blue skies, green plants, and the warm glow of suns like ours. But maybe that's the mistake. Maybe life doesn't care about beauty or color or comfort. Maybe it simply adapts to whatever energy the universe offers. If the living world of K2-18b is real, it isn't a twin of Earth. It's a reminder that the cosmos writes its own rules. A black ocean breathing under a red sun might seem alien, but it could be the most common story in the galaxy. So we have to ask ourselves, are we searching for life or just for a reflection of ourselves? Because if life can thrive in darkness, maybe we've been looking for the wrong thing all along. Deep beneath K2-18b's heavy atmosphere, sunlight may never reach the ocean at all. Instead, the true story of life there could unfold in the dark. Powered not by light, but by chemistry, scientists believe that where intense pressure meets searing heat, a network of hydrothermal systems could exist, much like the black smoker vents on Earth's seafloor. On our planet, those vents are home to entire ecosystems that live without the sun. Microbes there draw energy from chemical reactions between water and minerals, creating the foundation for a food chain that thrives in total darkness. The same principle could apply on K2-18b. The immense pressure from its atmosphere, combined with geothermal heat from its interior, might produce deep-sea environments rich in hydrogen, methane, and carbon compounds. The raw ingredients of life. Computer models suggest that as water sinks into the mantle of K2-18b, it could react with the planet's silicate crust, releasing hydrogen and forming energy-laden molecules. These reactions might sustain chemotrophic organisms, life forms that feed on chemical energy instead of light. Some scientists even speculate that the intense compression could turn carbon into layers of diamond rain, creating exotic weather patterns that constantly reshape the deep ocean. If that sounds strange, remember that Earth itself once looked no less impossible. Before photosynthesis evolved, our earliest life forms were chemotrophs, microbes living off volcanic gases and metal-rich vents. K2-18b maybe a time capsule of that ancient stage, a planet where evolution never needed light to begin. And because its red dwarf star is so stable, this process could have been running uninterrupted for billions of years. Imagine what that means. A biosphere that has had an unimaginably long time to adapt, specialize, and evolve intelligence under alien conditions. Life that has never seen the surface, never needed eyes, and never measured time by the rise of a sun. Could such creatures exist today in the depths of K2-18b's eternal sea, beings that sense chemistry the way we sense light? If evolution has been quietly unfolding for billions of years, intelligence might not look anything like ours. It could think in molecular patterns, communicate through pressure waves, or build networks invisible to any telescope. K2-18b challenges us to imagine life not as fragile or rare, but as relentless, capable of surviving in crushing darkness and feeding on stone itself. And that leads to one haunting question. If life has been evolving there since long before humanity existed, just how intelligent might it have become? K2-18b orbits a red dwarf star, one of the most enduring suns in the universe. Unlike our yellow sun, which will die in 5 billion years, a red dwarf burns so slowly it can live for trillions. That means K2-18b isn't just stable for a while, it's stable almost forever. In cosmic terms, this planet could still thrive long after our solar system turns to dust. Compared to Earth, the difference is staggering. Our species is still in its cosmic childhood. Civilization has existed for only a few thousand years, barely a blink of time beside K2-18 star. That immense timescale gives life their one unmatched advantage: time to evolve, to change, to perfect itself. If microbes formed in K2-18b's oceans billions of years ago, they may have had longer to develop than anything on Earth ever will. Evolution could move slowly, uninterrupted by impacts or extinctions. Under a red sun that never dies, life would enjoy the luxury of eternity. But the light reaching the James Webb Space Telescope isn't showing us K2-18b as it is. It's showing us as it was 120 years ago. Every molecule and chemical signature we detect is already history. The DMS we see now could have been made by organisms long gone or transformed. We aren't witnessing their present. We're peering into their past, reading an ancient photograph that can never change. In astronomy, every discovery is already a memory, so when we say K2-18b might host life, we're really saying it once did, at least a century ago. The next decade may be the most important in human history, because for the first time, our technology is powerful enough to see life beyond Earth, not just guess it. The James Webb Space Telescope will continue observing K2-18b through 2026, targeting its atmosphere again and again to confirm the mysterious dimethyl sulfide signal. But Webb is only the beginning. NASA's upcoming Nancy Grace Roman telescope, set to launch later this decade, will scan thousands of exoplanets using coronagraphs capable of blocking a star's glare, allowing direct images of alien worlds. On Earth, the Extremely Large Telescope, ELT, in Chile, with a mirror 130 feet across, will break every record for precision. Its instruments can separate starlight photon by photon, revealing surface patterns, clouds, even storms on distant planets. And then comes the real revolution. Scientists are now developing the concept of a solar gravitational lens, a mission that would send a probe far beyond Pluto to use the sun's gravity as a cosmic magnifier. In theory, it could capture images of exoplanets like K2-18b with resolution down to individual continents, or in this case, ocean currents. For the first time, humanity might see the color of an alien sea. Meanwhile, artificial intelligence is changing how we read those signals. Machine learning systems are now being trained to recognize the chemical fingerprints of life. Subtle combinations of gases, reaction cycles, and heat patterns that human eyes might miss. These AIs can run millions of atmospheric simulations in hours, predicting not only whether life exists, but what kind of life it might be. Some models already suggest forms of metabolism that match the DMS anomaly Webb found. Soon, these technologies will combine space telescopes, ground observatories, and AI supercomputers to give us our first true portrait of another living planet. It could happen within our lifetime, perhaps even within the next few years. But that possibility comes with a question that feels heavier than any discovery so far. What happens when we finally see something alive on another world? Something that moves, breathes, or reflects the light of its red sun back at us? Will humanity be ready to face what looks back? Or will we realize, too late, that the universe has been alive all along, and we were never truly alone? For generations, we've searched the stars for another Earth, a second home, a reflection of ourselves. But K 2-18 B is an Earth 2.0. It's something far stranger, a world of black oceans, hydrogen skies, and light that never truly shines. If life exists there, it follows rules we've never known, evolving in silence beneath an eternal red glow. This planet forces us to rewrite what alive really means. It shows that life might not need continents or sunshine, only chemistry, pressure, and time. If James Webb's data is confirmed, it won't just prove that life exists elsewhere. It will prove that life can adapt, endure, and thrive anywhere the universe allows it. K2-18b could mark the dawn of a new era in astrobiology, one where we stop searching for familiar blue worlds and begin to recognize that the cosmos may already be teeming with life, hidden in shapes and systems beyond our comprehension. The universe may never have been silent. We just didn't yet know how to listen. So, what do you think? Are these traces the fingerprints of alien biology or something beyond our understanding? Subscribe to Mind Gap, because this may be the moment humanity finally learns we were never truly alone.